This is part 3 of the opening lectures on the theory of special relativity. At the end of part 2, I derived for us, using Einstein's very famous Gedanken experiment, the equation that is known as time dilation. Once again, to summarize that expression, we have the following. Imagine that you guys are a stationary reference frame, and according to you, I am moving. So according to you, my clocks are running slower than yours. Less time is elapsing for me than it is for you. I am literally aging at a rate that is less than you. However, according to me, it's backwards. According to me, it's you guys that are moving. So then therefore, according to me, it's your clocks that are running slow. According to me, less time is elapsing for you than it is for me. You are aging at a rate that is less than me. Both of us are correct. Now, how can we possibly begin to visualize all of this? Let's go ahead and take a look at an opening example. Copy down example number 1, please, into your notes involving this journey that is made by a starship from the Earth to Alpha Centauri. Okay, so here is that problem. The starship travels from the Earth to Alpha Centauri. That system is 4.3 light years from the Earth, and it does so at a speed of 90% the speed of light as measured with respect to the Earth. So let's begin to draw this out. Okay, right here is the Earth. Right here is Alpha Centauri. The two objects are in the same reference frame because they are not moving relative to each other. The distance between the two, this is referred to as L, is 4.3 light years. Okay, now recall that a light year is not a unit of time, it is a unit of distance. It's the distance that light travels in 1 year. It's about 6 trillion miles. It's about 9.5 trillion kilometers. Okay, now how would you describe event number 1? Well, think of event number 1 as the starship leaving the Earth. So, for example, here's our starship. Hopefully you guys recognize that theme song. If you don't recognize that theme song, then your background in science fiction is sorely lacking. Okay, now the speed of the starship relative to the Earth Alpha Centauri reference frame is 90% the speed of light. Okay, event number 2 is that the starship arrives at Alpha Centauri. So once again, here's our starship. Once again, I hope you recognize that theme song. Okay, now in part A of the problem, we have the following. According to observers in the reference frame of the Earth and Alpha Centauri, how long does the trip take? Because the two events, according to the Earth Alpha Centauri reference frame, occur in different locations, then observers in that reference frame would measure an improper time interval. Now, very simply, speed equals distance divided by time, where this is the improper time interval that we're asked to measure. So this is then therefore the amount of time that goes by in the Earth Alpha Centauri reference frame. Therefore, the people in that reference frame will age the amount that we're about to calculate. Now let's just go ahead and cross multiply to do so. Delta T improper is L over U. And then what about the units? Well, I could keep all of the times in years and all of the distances in light years as long as I get the speed of light correct. In other words, what is the speed of light in terms of light years per year? Well, it's 1 because that's the definition of a light year. The definition of a light year is the distance that light travels in 1 year. So then therefore the speed of light c is 1 light year per year. And now let's just go ahead and plug in and calculate delta t improper. So here's what the numbers look like. We have delta t improper is equal to, first of all, L, 4.3 light years, and then divided by U, which is 0.9 times C, so 0.9 light years per year. Notice that light years cancels out, and we'll end up then with a time in terms of years. So I have here then 4.3, there we go, divided by 0.9, and this works out to be about 4.78 years. So observers in the Earth Alpha Centauri reference frame, they age 4.78 years. Okay, now let's take a look at part B. Okay, now for part B, this is according to observers on the Starship. So according to observers on the Starship, how would you then describe the two events? Well, imagine, for example, sitting in a room on a Starship, and let's say that you happen to have a window so you could watch what happens outside. According to your reference frame, how would you describe the first event? Well, event number one, according to that reference frame, would be that the Earth leaves. And then the second event, according to that reference frame, would be that Alpha Centauri arrives. So now for part B of the problem, this was part A earlier, of course. For part B of the problem, we would now describe event number one as the Earth leaves. And then we would describe event number two as Alpha Centauri arrives. So in part B of the problem, it does ask us to identify the two events, how we would describe them. That's how we would do so. Now, according to an observer on the Starship, the two events, the Earth leaving and Alpha Centauri arriving, occur in the same location. Think of it like this. Let's say that I've got this meter stick here. Right here is the Earth, and right here is Alpha Centauri. And I'm sitting on a Starship. It's as if we're just sitting here in this room, and we're looking out the window. And then therefore this meter stick is going by me at 90% the speed of light. Event number one is that the Earth leaves, and event number two is that Alpha Centauri arrives. According to me, the two events occurred in the same location, therefore I measure a proper time interval. Now we can calculate the proper time interval because earlier we had measured the improper time interval to be 4.78 years. We'll use the time dilation equation on the top board in order to do so. So now delta T proper is equal to delta T improper, 4.78 years, and then multiplied by the radical. 1 minus 0.9 c quantity squared over c squared. Notice how I'm writing the radical sign here in terms of c. Notice that all the c's underneath the radical sign will cancel out. So then therefore I end up with 4.78 years. It's still here in my calculator, and I'll multiply now by the square root of 1 minus 0.9 squared. And that works out to be about 2.08 years. So according to observers on the Starship, the journey only takes 2.08 years. So then therefore people in the Earth Alpha Centauri reference frame age by this amount, whereas people on the Starship age by this amount. So if you were going to do a journey like this in practice, would you try to bring enough provisions like air, food, and water and so on to last you 4.78 years? No, because according to you on the Starship, only 2.08 years goes by. Therefore, you only age this amount, whereas observers in the Earth and Alpha Centauri age this amount. Okay, now think carefully about the following question. According to part B of the problem, remember how I described this. I did so by using this meter stick. This meter stick is going by us at 90% the speed of light. Event number one is that the Earth leaves, and event number two is that Alpha Centauri arrives. It only takes, however, 2.08 years for that meter stick to go by. Therefore, is that meter stick still 4.3 light years long? No, it is not. Now let's take a look at part C. Part C says the following. According to each reference frame, what was the distance traveled? So take a look on the top board still for part A of the problem. According to the Earth Alpha Centauri reference frame, the distance between those 2 points is 4.3 light years. That's the distance L as we correctly described. But now according to observers on the Starship, if this meter stick is going by you at 90% the speed of light, and it only takes 2.08 years for it to go by, can it still be 4.3 light years long? No. The length has to be shorter. The length has to be contracted. This is the flip side of the coin, if you will, to time dilation. This is referred to as length contraction. Okay, what we're going to calculate here in part C is referred to as L prime. This is the length of that meter stick, if you will, according to observers on the Starship as it goes by at 90% the speed of light. Now, how do I find that distance? Well, speed equals distance divided by time, where the time is the proper time interval that we found a few minutes ago. So now let's go ahead and cross multiply and solve for L prime. So the distance L prime is u times delta t proper. So this is equal to 0.9 light years per year multiplied by delta t proper, we just found that a moment ago, to be 2.08 years. Notice that the years cancels out like so, and we'll end up with a distance here in terms of light years. So 2.08 years, it's still here in my calculator, multiplied by 0.9 light years per year, and this ends up being 1.87 light years. As I said, this is the flip side of the coin to time dilation. This is referred to as length contraction. How is this L prime that we just found here in part C related to the original L up on the top board? The two expressions, or the two lengths, if you will, are related to each other in the following way. Take a look at this expression right here for L prime. But now let's go ahead and replace the delta t proper from that expression with the time dilation equation above. When we do, we end up with the expression for length contraction. Okay, so from the expression on the right-hand board, L prime is u times delta t proper. And now replace the delta t proper with delta t improper multiplied by the radical sign. Like so. And then take a look at this right here. Compare this right here to what I wrote down earlier in part A of the problem. Notice that u times delta t improper is equal to the length L. So then therefore, the contracted length is equal to the uncontracted length multiplied by the radical sign. L prime, the contracted length, is less than L. So here's basically what this expression is saying. For example, let's say that you guys are stationary and I am moving relative to you, and I have a meter stick. According to me, the meter stick is stationary, so I measure its length as L. However, according to you guys, not only are my clocks running slow relative to yours, but my meter stick is contracted in the direction of motion. You guys measure the length as L prime. But now let's say, for example, that you guys have a meter stick. The meter stick is motionless with respect to you, so then therefore you measure its uncontracted length L. However, according to me, not only are your clocks running slow, but your meter stick has a contracted length L prime because your meter stick is moving relative to me. And now you may be asking yourself the following. Well, is the meter stick really contracted in the direction of motion, or does it just look that way? There's no difference between those two questions. And the reason for that is because what is the only means that you have available to you of measuring the length of a moving meter stick? Time it as it goes by. So then therefore, in part B of the problem, if the meter stick is going by you at 90% the speed of light, and it only takes 2.08 years for the meter stick to go by, then its length is 1.87 light years long. Length contraction and time dilation, as I said, are flip sides, if you will, of the same coin. And basically what the two expressions are saying is as follows. How we experience time and space depends upon how we are moving relative to each other. Now, why don't we notice any of this in our everyday existence? The reason why we don't notice any difference between L prime and L, or on the top board, delta t proper and delta t improper, is because of the radical sign. In our everyday existence, the speeds of ordinary objects relative to a reference frame is extremely small compared to the speed of light c. So the term u squared over c squared is essentially equal to 0 in our everyday existence, like so. So then therefore, if u over c, or u squared over c squared is basically 0, then L and L prime are the same thing, and then the time dilation equation, delta t proper and delta t improper, are the same thing. However, when u is a significant fraction of the speed of light, then these relativistic effects, they then become noticeable. Notice also that these equations tell us something else. They tell us that it's impossible for an object to move the speed of light or greater. For example, take a look at, first of all, the time dilation equation. Consider what happens if u is equal to c. If u is equal to c, then underneath the radical sign you have 1 minus 1, which is 0, and then therefore the proper time interval literally doesn't exist. So if an object can move the speed of light or greater, it would literally mean that time does not exist. Notice also that something weird happens if the speed u is in fact greater than the speed of light c. Then you end up with an imaginary number here with the radical sign, and that makes no sense in this context. Same thing for the length contraction equation. So imagine that an object is moving at the speed of light, so u is equal to c, and then therefore L prime is equal to 0. Therefore, if time doesn't exist for an object moving at the speed of light, nor does space. So these equations by themselves, they really don't definitively prove that it's impossible for an object to go the speed of light or greater. That comes a little bit later on in the theory, but they definitely do suggest that something is wrong. Let me go ahead and then pause the film here for part 3. We'll conclude with part 4 in just a few moments.